Hey everyone, welcome to the Physics Guy, and today we're going to start our F equal ma marathon for this year. To start, we're going to do question 2, which will have a part 2 for question 3 of the F equal ma 2025. To start, we are told that there are three identical disks, and they're placed on a frictionless table, and it's an elastic collision, and they collide simultaneously. And the third disk is launched with a speed v initial directly toward the midpoint of the two stationary disks along a path perpendicular to the line connecting their centers. To start, we can see the diagram, and we can see that theta is going to be 30 degrees. And that we can tell of this because of the triangle here, which is going to have all equal 60 degrees, which will be split up between those two disks. Thus meaning that its Vx is going to be cosine 30 degrees, and its y component is going to be sine 30 degrees of the velocity of the two disks. And since they collide simultaneously, we can assume that both of the disks' velocity will be the same. So to solve this, we will have to be using the conservation of energy since an elastic collision, and we will also be having to use the conservation of momentum. So to start with kinetic energy, we can see that it's 1 half mv squared initial, so the initial kinetic energy of the disk, and we can see that it's going to be the kinetic energy of the two disks and v1 both moving with the speed of v1, and then the after velocity, which we need to find, of the first disk with the initial velocity. Doing some algebra, we can see that v0 squared is going to be equal to this value, and we can cancel out the masses. It's no longer 1 half mv1 squared because we add both of the disks' velocity. And since kinetic energy is a scalar, without any components, we don't necessarily treat anything differently, and we just keep it its regular velocity. Now with momentum, mv0 is going to be equal to 2 cosine theta, and remember that theta is going to be 30 degrees, mv1 plus mv0 after. Each y component cancels out because they're simply equal. Now, after we do even more algebra, we can see that v1 is going to be approximately this value, and to finally solve the problem, we need to plug it in to the kinetic energy equation. To fully solve it, we get the answer D, and so it reflects back with 1/5 of its initial velocity.